real gases do not behave as ideal gases. And the reason is that the ideal gas law does not take into account the volume of a gas, and it also does not take into account molecular forces between gas particles. In the ideal gas law, it's assumed to have no volume, the gas, and the particles are assumed not to interact, which both are not true. So in order to accurately describe an ideal or a real gas as opposed to an ideal gas, I need to account for those two factors. The first one's easy enough to deal with. So I have P is equal to nRT over V. In order to correct for my volume, I need to find out the volume of my gas and then subtract it from the total volume, because in this ideal gas law, volume is the volume of the container. But if I take into account the volume of the gas, I take the volume of the container and then I subtract my volume correction factor. And that would be this. N is the number of moles and B is the volume correction factor, which is determined experimentally. So I don't need to worry about calculating it, I just look it up in a table. So that's the volume correction factor. Next is the pressure correction factor due to intermolecular forces. Pressure is not as high as it would be because of the intermolecular forces. Because they're assumed not to interact, the particles strike the surface of the container with maximum force. However, since they do attract each other, they pull each other off course and they either hit each other, or those forces, when they pull on each other, it's going to cause them not to strike the container with quite as much force. So this is the pressure correction factor. A is the pressure correction factor, N is moles, V is volume, and they're being squared. So I guess I should, well, yeah, I'll talk about where this comes from. So suppose I have some box. These are gas particles. So this factor is basically describing the amount of forces between the particles. So I have a bunch of particles in a box, one's exerting force, they could be attracted. These are the possibilities. One can interact with all of these particles. So I'm going to describe that as this, where N is the number of particles. Normally it's going to be in moles. So the first thing I'm going to do is I'm going to ignore the -1, although technically when I'm counting the possible interactions, I don't include one interacting with itself. Normally I'm going to be dealing with moles, and 1 mole is 6.02 times 10 to the 23rd. And 6.02 times 10 to the 23rd minus 1, for all intents and purposes, is 6.02 times 10 to the 23rd. So I'm going to ignore this -1. And just say that it's N. Now it does not stop there. 1 can interact with 2, 3, 4, and 5, but 2 can also interact with 1, 2, 3, 4, and 5. 3 can interact with 2, 1, 4, 5, and so on for however many gas particles. So the total number of possible interactions is going to be this number squared. Because if 1 were to be included, then the number of possible interactions would be 5 for 1, For 2, the number of possible interactions would be 5. 3, the number of possible interactions would be 5. So it's 5 times 5, if I were to use this example. So it's going to be squared. And although it's technically n minus 1 because 1's not included, but we're not included. I'm not going to include that. So n minus 1. Now, that being said, it's not going to be precisely n squared, because when I do these interactions 1 to 2, 1 to 3, 1 to 4, 1 to 5, I'm going to start getting repeats. When I start going on to 2, 2 to 1. I've already done 2 to 1 when I did 1 to 2. So that's not counting. Then 3, I'm going to have even more. I'm going to have 2 to 1, and then 3 to 1 I've already done. And then once I get 4, then more than most of them have already been done. Once I get to the last one, all of them except for 5 to, well, all of them, almost all of them have already been done. So, in order to account for that, I need to divide this by 2. And now my correction factor is this right now. Then I go back, and it's starting to look more like this, and that's where the n comes from. That's all that's really important. And the volume is included because if the concentration is also just as important as the number of molecules for the interactions, because if the volume is very large, then the interactions, this correction factor isn't going to have much of an effect, because the volume being is very large, then the chance for an interaction is very low. But if the concentration is very high, then it gets closer and closer to being just n, I guess. Just, I was rudely interrupted, but anyways, where was I? Oh yeah, this, yeah, the pressure correction factor. So yeah, I've already explained it. Okay, so now that I have the pressure correction factor, I need to combine the volume correction factor and the pressure correction factor into one. So I have my observed pressure. And the volume correction factor. And then I'm going to subtract the pressure correction factor. I'm terribly sick today. And A and B are going to depend on the gas. I just looked them up. I can't really calculate them. They're determined experimentally. But anyways, this is technically a correct form. However, the more common way I'm going to see this is in the van der Waals equation form. So I'm just going to multiply both sides by V minus, yeah, I'm terribly dyslexic, what the hell, NB, oh, yeah, whatever, multiply both sides by V minus NB, and I get pressure is equal to NR. I forgot. Yeah, well, that's what happens when you get distracted from things. nRT minus A NV squared times V minus NB. This is one term. I'm going to add it to the other side. And I can factor this out and then just write in a simpler form. This is the real gas equation, or it's often called van der Waals equation.